All right, Algebra 1A students, welcome to part 2 of your video on lesson 6.3. Today we're going to continue talking about solving systems of equations with elimination, but we're going to do one extra step in this video that we will run into quite often when we're trying to deal with solving a system of equations. Sometimes when we solve a system of equations, we're not given a system where one of the variables has the same number in the front in each equation, which we've been seeing in the past few days while we've been practicing elimination. We've always been given a system of equations that's set up very nicely for us to eliminate. That's not always the case, and sometimes when we solve a system by elimination, we have to first multiply one of the equations by a number to make the number in front of a variable the same. What that looks like is something like this. So if I have this system of equations over here, negative 2x plus 15y equals negative 32, and 7x minus 5y equals 17, notice that my x coefficient numbers are 2 and 7. Those aren't the same. And my y coefficient numbers are 15 and 5. Those are also not the same. So I have to multiply one of these two equations by a number to make the numbers be the same. And we have to decide what variable number could we multiply to make it the same as the one in the other equation. What I hope you can see here is I could turn this 5 into a 15 by simply multiplying it by 3. Right? If I multiply this by 3, I will get a 15. 3 times 5 is 15. So what I do is I put this entire second equation in parentheses. And then I multiply the 3 by every single piece that's in the parentheses, just like the distributive property that we've done so many times. What I end up with, 3 times 7 is 21x minus 3 times 5 is 15y equals 3 times 17 makes 51. So that's now my bottom equation. All right. Now, if we look at the top equation, we should realize now that my 15y and 15y will cancel out, right? So I've basically replaced this equation here. I don't want that anymore. I'm looking now at these two equations. Now, positive 15 and negative 15 have different signs, so when I have different signs, I'm going to add the two equations together. Remember, skipping over this middle guy. I'm going to do negative 2 plus 21, negative 2 plus 21, which gives me 19x. We know that the y's should go away because positive 15 plus negative 15 is nothing. That goes away. The other side of my equal sign is negative 32 plus 51. Negative 32 plus 51 gives me a positive 19. And now I have an equation set up that I can solve actually relatively easily. I can divide this by 19. That goes away. I can divide this by 19. I get that x is equal to 1. Right? X is equal to 1. Now, we know I have to also find the y value for this system of equations. So I'm going to box in my x equals 1 because I know that's part of my answer. And then I'm going to put it back in to this equation up here and see what I get for my y. Negative 2 times 1 plus 15y equals negative 32 is what my top equation says. If I replace the x with the number 1, I get 2 times 1. That, of course, is just negative 2 plus 15y equals negative 32. And then if I want the y all by itself, I'll start by adding 2 on both sides. Right, and I get negative 30. The other side is a 15y still, but now the 2 is gone in the front. And if I want to get the y totally by itself, I just have to divide off the 15 here. So I divide this side by 15. That goes away. And I divide this side by 15. And I get that y is equal to negative 30 divided by 15 is negative 2. So my final answer then, as a coordinate point, x was 1, comma, y is negative 2. And there's my final answer. Okay, so that entire process was exactly the same as what we have done previously, except now I have that extra step in the beginning, remember, where I had to multiply the whole equation by 3 in order to get the number in front of my y variable to be the same. But once I had that, the process was exactly the same. I add because I had different signs. I solve for x, I plug it into one of the equations, and I find my y value. Okay? Now, if we do one more example, something that we might see in our practice problems. This system of equations here. 3x plus 4y equals 13, and negative 9x minus 12y equals 25. Again, I want you to notice that my two equations do not have the same number in front of either the x or the y. 3, 9, 4, 12, not the same. But I think I can turn the 3x's into 9x's simply by multiplying this entire top equation by 3, right? If I do that, and I multiply the 3 into all of these pieces, by the way, just because I multiplied this one by 3 and I multiplied this one by 3 doesn't mean I'm always going to do that. You just have to decide what number do you have to multiply by to make the numbers in front the same. So if I multiply this by 3, I get 9x plus 12y equals, that's 39. And now I have an equation that's the same as this one. I just multiplied it all by 3. And I can now eliminate my x variables, a positive 9x and a negative 9x. I can get rid of those by adding together these two equations because they have different signs but the same number. Different signs means I add. When I do that, my x's go away because that's what I was trying to do. 9 plus negative 9 is nothing. But also look at my y variables here. I had 12y and I'm adding a negative 12. Well, adding a negative is like taking them away. 12 plus a negative 12 gives me 0y. Right? 0y. So that's also totally gone. Poof, totally gone. So my x's are gone, my y's are gone. All of my variables have disappeared. I have nothing left on the left side of my equal sign. And on the right side, I'm supposed to add together 39 plus 25, which gives me 64. Okay, so now look at what's left here. And I'm supposed to be solving for one of my variables, but I don't have any variables left. So remember, when all of your variables disappear, you have two choices, right? No solutions or all solutions, and we decide that by looking at what's left. 0 equals 64. Is that a true statement? No. So I say no solutions. Okay? So sometimes we have a system of equations where all the variables disappear, especially when we have to multiply one of the equations. And when that happens, you look at what's left, decide, is this a true statement? 0 equals 64. Not true, so we say no solutions. Right? If it is true, if it says 0 equals 0, for example, that's a true statement, 0 equals 0, then we'd say all solutions. All right? If you have questions about multiplying one equation before you eliminate, or this idea of no solutions versus all solutions, please make a note to ask me in class tomorrow Otherwise, that's all I have for you. Have a wonderful night.